Guys, how are you doing? Today I'm going to review a new paper called Dynamical Stability of Kessence Field Interacting Non-Minimally with Perfect Fluid. This is my paper and I had written this paper around 2021 and it was published in November 2021. So the title suggests that Kessence field is interacting non-minimally with perfect fluid. So the problem is that I have already described the perfect fluid. That is the meaning I have already described in my other video, that what is the meaning of minimally and non-minimally, and also you can check out the video on Kessence, what is the Kessence field and how it can mimic the dark energy. For an example, we take a background fluid because we know that our universe is filled with dark matter and dark energy, in which dark matter is contributed to about 27% while dark energy is 69% and so on. Dark energy is played by some kind of field. Throughout the evolution of the fluid, we assume that the number of particles is always conserved and the exchange of energy taking place between the field and fluid directly and all the way, the entropy must be conserved. Okay, so the thing is that when we are talking about the non-minimal scenario, so we are defining an action. Now this action is carrying the Einstein's term. Here you can see the Einstein's term, and then here it is your fluid thing. Okay, so this fluid action was first introduced by Brown, and here you can see that square root of minus c is metric, rho is energy density which depends on the number density, and entropy, J mu is the fluid current. Okay, and phi mu, theta mu and alpha mu or beta a, they are the some Lagrangian multipliers which is actually associated with the physical physical quantities of the fluid, just like I told you, the stress tensor and all this not the shear components and all these things. Okay, now here I have taken the action corresponds to the Kessence where it is taking some kind of field phi, and it has the kinetic term which is non-linear, like x is equal to half d mu phi d mu phi. Let me rewrite here. So x here can be taken as half d mu phi, and we are assuming that this x term is always be positive. So here we have encapsulated the d mu phi, means that phi dot square is being encapsulated in x. So in some sense it is not a linear kind of theory, it has now become non-linear. Now the thing is that when we are talking about the non-minimal, what happens is that if we are ending our components till here, then what happens is that here it is a fluid which denotes the dark matter term, it's a dark energy component, and here is the metric term, the Einstein's term. So they are coupled minimally, means that they are actually transporting their energy, or they are talking to each other with the fluctuation on any metric. Okay, so their evolution is independent but they are interacting only gravitationally. But what happens when we try to introduce some other term which is consisting of the fluid parameters as well as field parameters? So we are labeling this term F, is actually giving you some kind of an interaction between field and fluid. So this interaction term consists of the fluid parameters as well as field parameters. Now in our case, since field has the both term phi and x term, and they are actually playing a role, and phi and x term are both independent, while on the other hand the fluid term is these are the very fundamental terms like number density and entropy. So we have packed our interaction with all these terms, because we don't know the nature of dark matter and dark energy. Okay, how they will interact, how they will give some different reactions, we don't have any idea. So when we don't know anything, in absence of the specific experimental evidence, what we do, we take our all ignorance in some kind of function, and we try to predict, or we try to build some model, and whatever we have the data, we try to fix them, and we want to say that okay, maybe this component is playing a crucial role, or maybe this component is playing crucial role. So this is the thing, we have every field there is a potential, and in Kessence the potential can be constant and cannot be constant. So here we have assumed that the potential is power law type of potential, and the best candidate is 1 over phi square. People have already done so many research using this kind of potential, and they have fitted with data. So we have already taken this into an account that okay, v phi is 1 over phi squared. Now we would try to study this approach using the Lagrange concept. Okay, in the previous video you can see that we have defined that, okay, suppose this is your energy momentum tensor, and if you take the covariant derivative, it will give you rho dot plus 3h rho plus p is equal to 0. And suppose you have the two t mu1 and t mu2, therefore there will arise a plus q term and minus q term, and together they will, energy momentum tensor is always conserved. So this q term will decide that where the energy is, one candidate can lose energy and one candidate can gain some energy. Okay, so this was not a great approach. It is, we cannot say that, okay, this is the only approach you have to rely on, and this is not a very generic one. So what we have done is that we have started from the very fundamental thing that is called define the Lagrangian, define the action, and it will give you the complete dynamics of total system. And it, in some sense, it is constraining your system that you cannot choose any kind of f. There has to be some validity how you're going to choose your f. Okay, and now here there was no any guiding principle to choose q. If you are just defining at this point, you are simply giving you something, you are assuming, you are guessing some models and so on. But here we can have the dimension of f, and there are different things. Now here you can see that rho has a dimension of m to the power 4 if I am taking the mass dimension. Similarly, j mu will have the m to the power 4 dimension, and except j mu and this whole quantity will have m to the power 4 dimension. Similarly, this Lagrangian will have m to the power 4 dimension. So we can say that this f will have the mass to the power 4 dimension. While there were nothing like here q, you can choose any kind of dimension, although here is again a guiding principle that it must be aligned with rho dot, that q must be there. But there were no any guiding principle that you must have some kind of degree of freedom and all these things. So here everything comes that how much degree of freedom it should have, or does it give you some a consistent way of framework or not. So let us let us proceed and see what happens. As we have defined that in the Lagrangian of the field, it is contributing with this del mu phi, and it is nebula because we are talking about the covariant derivative. And now since phi is a scalar quantity, therefore all d mu can become simply d mu. Okay, now our choice of metric is simple. It is d2 square minus plus 8 dx squared. Okay, so this is the FLRW metric, where we have assumed that our universe is isotropic homogeneity. So no matter where you look, your universe seems to be same in all possible directions. Okay, so now what is the interesting thing about the fluid? Now interesting thing about the fluid is that the current density. Okay, now this current density is actually defined in terms of fluid velocity, and this fluid velocity is labeled as u mu, and here u mu we have taken is 1, 0, means that it has one a time component and there is no any space component. It means that whatever the fluid velocity, it is actually having the same kind of evolution. It is evolving with time. So u mu is usually defined as dx mu over dt, and when mu is 0, therefore dt becomes dt and it will be 1. So, and now we are considering that there is no any space component. It means that there is no any inhomogeneity in a spatial component. N is the number density. So this current density is basically encapsulating your number density. So here if you want to take the magnitude of it, you can take the magnitude like that, and from here the number density can be defined like this, and you have the u mu. These are the normalization constant of the field velocity, that if you contract the u mu with u mu, contravariant and covariant, then you will always get the negative of 1. Okay, so these are the very basic thing, and out of the basic thing we have defined our energy momentum tensor, which is usually the standard definition of energy momentum tensor is that T mu nu is equal to minus 2 over square root of minus g delta s over delta g mu nu. Okay, so for the perfect fluid we have this T mu nu for the matter part. Okay, so now since we have the action, and if you just varying this action with respect to g mu nu, you will get the T mu nu corresponds to the only fluid part, means that square root of minus g and j mu of this thing. So you will end up with the rho u mu, and there is term this n d rho by d n minus p u mu u nu plus g mu nu. So usually what you see if you are taking any standard fluid, you will see that this part and this part, and multiplying with this part. So you label is that if you comparing with this thing, you can say that okay, this part is pure density term and this part is the pressure defined for this relativistic fluid. Okay, so P is equal to always n d rho by dn minus rho. I hope it is clear. So here is the pressure of the relativistic fluid, and again we have taken the FLR double background metric, and if you vary this action with respect to field your phi, so suppose you have the field phi and x, these are two independent quantities, but as you can understand from the mechanics, classical mechanics behavior like that, suppose x is your coordinate and x dot is your velocity, these are the important quantities. But if you vary your Lagrangian with respect to x and you take the total derivative, you will get the you will just have to vary this one quantity dx and you will get the Newton equation or equation of motion. The similar thing happens like here. So these are very 20 years old and you can easily find anything. The extension is that we will have not studied till now. Kessence is talking to dark matter directly. So there is exchange of energy momentum tensor through the metric, as well as they can interact directly. Then what happens? What kind of things can grow and things can become? So the field equation will be modified. So if there is no f, then there were no any equations such that. But when we have introduced the extra term, then we are having this interaction term that f cross phi, f dot phi will give you f comma phi will give you basically df over d phi. Okay, and similarly here that del mu f comma x is again df over dx. Okay, so these are the derivative terms. Now here we can we have to apply the usual general relativity theorems like del mu, a mu nu. Suppose you have the any vector quantity and you want to take a covariant derivative, then you have to expand using the Christoffel symbols or connection term. Okay, so in this case we can also derive the energy momentum tensor corresponds to this field, and this field will give you the energy momentum tensor for corresponding towards the field. This is the field which is usually find in the text standard research papers, and from here we can find easily that what is the field density and what is the pressure. Similarly for the interaction term corresponds to I, so you have to do everything just you do with the standard fluid and standard field. So similarly you vary this thing and you will get the energy momentum tensor corresponds to interaction, and it is consisting with n df dn u mu u nu. So it does telling you about something like rho. And similarly again the pressure of the energy momentum tensor of this interaction, that it is having the interaction pressure, and some off terms. Okay, but because if you will define the velocity of any kind of field, then this velocity is actually defined like maybe d mu phi over square root of x or maybe something. Okay, I am forgetting right now that we define it. Okay, so basically in our case this x will become 1 and you will always end up with this kind of velocity. So they are the part of density, so this will become the density. And in our case the field velocity and fluid velocity, they coincide because there is no any perturbation. So we can say that the field and fluid are co-moving with the same in same direction, or let us say one can say that yeah, they have the same velocity as the time goes on. So in this case you can see that this rho interaction will become f minus 2x f comma this 2x will come from here, and p interaction becomes n df and minus f. So it has again the same kind of structure, that the effective rho will become like this one and this one. So you will have the effective rho and the effective interaction. Okay, so now what we can do here again, therefore this energy momentum tensor will consist of these three terms, like it will have the field term, matter term, and as well as the interaction terms. Now we can also have the multiple components here, just like j mu, phi mu, theta comma mu, and the alpha. So these are again important parameters, and from which we can vary our action. So these are the independent quantities. So considering that j mu is our independent quantity and varying this, so you will get these equations to be 0. Again, if you vary the action with respect to entropy, then now your entropy gets changed because you have the interaction term and again the contribution from the d rho by ds and as well as df by ds. Okay, now if you will take the phi, ds over d phi, which will give you that j mu u mu nu, and again j mu is defined as n u mu. Okay, so you will actually getting is that this is comma mu, so it will tell you that the number density is conserved in here. Okay, so now if you take the theta, you will get s j mu comma mu, which is again telling you that s dot is equal to 0, which is actually constraining your fluid equation to be adiabatic. So if the equation we are assuming that adiabatic, then this constraint need to be followed. Again, there is another constraint. So these are the constraints provided by the different parameters. So in this way that we can say that our fluid is are acting as a perfect fluid. So for perfect fluid, there are the conditions like n dot plus 3 and h must be always 0 and s dot is always be 0. So if you have this quantity, then you will always have the perfect fluid. Okay, so now we can define the chemical potential corresponds to this fluid. Mu is equal to d rho by dn, and in mu interaction again it will follow the same, that mu interaction is df by dn. So far what you are seeing here, that this j mu, basically the same thing here I have written del mu and u mu and del mu and s u mu. Okay, so it will it will give you the few different things like n dot plus n s dot plus ns and 3h is equal to 0. So n dot will give you basically minus 3nh and plus ns dot plus ns3h. Okay, so here again it will have some s, and what you will understand here, that if you just divide 3nh, this will cancel out and n cannot be 0, therefore s dot becomes 0. So basically this constraint is manifesting that you are having the adiabatic, you are in the adiabatic scenario, the entropy exchange between the field, fluid or gravity is nearly constant. Okay, g mu nu is equal to total t mu nu, and this t mu nu is consist of these three parameters, and we already know that this g mu nu has to be has to follow the Bianchi entity. Therefore all the energy, the total energy momentum tensor will also conserved. So now for this case we have to see that either our what kind of equation will it give if this case happens, that if you take that covariant derivative for delta t mu nu, the energy momentum tensor is conserved or not. Okay, so for that purpose we have redefined our t mu phi with the minus of this one, because here in equation number 10 we are getting that another case which is f comma x d mu phi. So for that purpose what we have done, because these are algebraically sum, so we can redefine our t mu phi as t mu phi minus this one. So for that purpose we are again redefining our another thing like t mu m, because it was left with a t mu m and t mu interaction. We have defined t mu nu tilde, and one need to add again f comma x d mu phi d mu phi. So in such a way that these two things they have to be really same, because t mu interaction again carry this term, and if you expand these things and these things, then this cancel and you will always get this negative term which is the part of this t mu interaction. So in some sense your t mu total is always be identical irrespective of how you are going to define this t mu prime and t mu tilde. So our field equation will become g mu nu is equal to kappa square t mu nu dash plus t mu nu tilde, and where kappa square is 8 pi g. So now if you take the covariant derivative in the right hand side, so what we are seeing that if you take the covariant derivative and you do the whole calculation, it is a very big calculation, I cannot describe each and every step. So what you will get, that here you will get f comma phi d nu phi minus f comma x, this one. So here is another term arising from only this part, and the similar term, because delta mu g mu nu has to be 0, therefore another term will arises from t mu nu tilde will become minus df by d phi del nu phi minus df by dx del nu x. So this is exact opposite to this minus q nu term. Okay, so in this way, because now I have written here delta nu x, and here it was written in the del nu phi. So if you convert it, then it will take another minus sign here and it will become plus. So never think that they are not looking same. It does not mean that they are not same. They are actually same if you just open the bracket. So in this way, that wherever we have got here the q nu part, which is exactly same as minus q nu. Therefore, in some way, in some sense, we can say that our delta g mu nu is following the Bianchi identities, and the right hand side is also conserved. So each and everything is, perfect, and this q nu term is actually basically giving you some extra terms, and this extra term is actually acting like an extra force in this thing, because that you have the interaction, and this interaction is imposing a force in this thing. And because of this non-trivial issue, it means that this is the term which is responsible for the exchange in energy between the field and fluid. As you can see that del f by del phi, if f is independent of phi, then it will become 0, and if it is f is only dependent on x, then again this term survives. But if you take f and x to be independent of phi and x, then q nu part will be 0. Therefore, if we can see that if f is not depend on x and phi part, there is no any extra term, there is no any q term arises, because we have already given the constant that 3n dot plus 3ns is equal to 0 and s dot is equal to 0. It means that if f is independent of n phi and x, therefore it is again becoming something kind rho. So you are just adding rho plus f, where these quantities are same, so it does not have any effect. So okay, so when it will have contribution, when you got the whole things like n s phi comma x, now again it is a kind of a very different quantities. Therefore it shows that now energy moment tensor is conserved, not the individual energy momentum conserved. Okay, now we have in the background, if we are imposing ds square is equal to minus dt square plus e square dx square, and if you expand the first Friedmann equation, you will end up with rho corresponds to fluid, field, and the interaction part. Now similarly here, that we are getting the second Friedmann equation, which is consisting of pressure, and again the pressure coming from the interaction part as well as field, and so on. So here is again the same thing, like energy density of the field. And now we can define the few new parameters like equation of state, as we have already defined in my previous videos, that if you take the ratio between pressure and density, you will always end up with the equation of state. And now whenever we are using the non-linear aspect of field, like whenever you have the non-canonical theory, this kind of, whenever you have the any kind of Lagrangian which is consisting with the phi and some non-linear aspect like x, so this can be simple Kessence, or maybe tachyon field, or maybe some different field. Okay, so then again there is some kind of contribution coming from the sound speed, that what is the speed of Kessence sector, and this Kessence sector speed is actually coming from when you take the perturbation in x. So usually it should come when your metric is perturbed, where you when you are defining your metric in such a way that there may come from an isotropic terms. But usually what happens is that since your Lagrangian is consisting with this nonlinear term, you can simply take a derivative, and it should be fine. There is no any problem if you define the sound speed in the case. So it is very common to define the sound speed. Okay, so we assume that whenever you have the field, the sound speed is positive, then we can have this you can have the proper theory. And if your sound speed can become negative, okay, or become negative, so cs square have several conditions. Like cs square is less than 0, we can say that okay, this theory won't work. Cs square is equal to 1, so it has the sound speed. And if it is 0 to 1, it means that it is not violating causality. But if cs square is greater than 1, it means that it is the velocity of propagation of the any fluctuation is arising in the Kessence can exceed the speed of light, which corresponds to superluminal speed, which is kind of contradicting, because nothing can propagate greater than light. But these fields are very non-linear, and in non-linear theory one can easily have the speed greater than 1, so there is no any problem with it. Okay, now again in our theory here also, that cs square can become greater than 1, and because we have not generalized perfect way, that if you have the if you have any kind of perturbation present in your one field, and whenever you have the fluid which has the pressureless fluid, how the perturbation is actually flowing through the interaction part and disturbs the fluid part. So we have not established that theory properly. So what we can we can simply generalize it that, okay, you can just take dp total over dx and d rho total over dx. If you just expand the whole term, then you will understand here that the the field equation will look like this one, that it will carrying the derivative of the Lagrangian with respect to phi, which is corresponds to the potential term, and again phi dot term, and again some derivative with respect to x, and you can see the lot of derivative, like double derivative with respect to the x, and again there is a cross term present here, that phi comma x, again there is a second partial derivative. So there are so many partial derivative terms have been taking place, and therefore the dynamics is kind of quite out of our hand, that by using your hand you can solve this equation. No, either you have to take the so many approximation, or it's kind of hard to solve this. So for that purpose, what we have done is that we have used the dynamical system approach. Okay, so in the dynamics, now the whole physics is completely clear to you. So you have defined the Lagrangian, you have found the energy momentum tensor, and you have found that individually they are not zero. When they will be zero, when the total energy momentum tensor can be zero, and you found the field equation. So together this, and following the constraint like the number density must be conserved, and there is no, and the entropy is also the whole system is an adiabatic regime. Therefore we are now converting each and everything to the dynamic system approach. Now from here the complete mathematics start. So in the case of dynamic system, we first define few variables. So now these few variables are defined like this, that so for phi dot here you define x, and now since here the phi is m inverse, first of all you have to find the dimension, and I have already talked about how to find the dimension in the dynamic system analysis. First you have to define what is the dimension for each and every quantity, and now you have to construct that what could be the dimensionless quantities in such a way that it must be closed system. So the best thing we can do is that first define x is equal to phi dot. T is having the mass inverse dimension, so d phi over dt will always be dimensionless. Therefore I have defined x is equal to phi dot. This is very standard. Again similarly for y, and sigma is corresponds to the fluid term, it is a fluid term, and then z, because z is carrying fluid terms as well as the field terms, so you have to define different quantities, like z is equal to kappa square f over 3h square. One way to look for this kind of system is by the by looking at the Friedman equation. As you can see here, that 3h square, when you define 3h square like this, so you will find that k square by 3h square and rho plus rho phi plus rho interaction. Now rho phi is carrying the lot of terms like rho phi is having b phi also, and 2x f comma x. Okay, and again if you're talking about the rho interaction part, therefore rho interaction part is having also a lot of interesting part, that it is consisting with f minus 2s fx, and again p interaction, it has the derivative term with respect to n. So in some sense you have to define these quantities using the idea of Friedman equation, that how we can choose. So we have associated two quantities like x and y corresponds to rho phi, and I have associated with z that kappa is square f by z. Now using these three quantities, if you know these three quantities, we can easily find this quantity. So this quantity is sigma square, so sigma square can be written as 1 minus x, so whatever it is, x minus y square and z square. Okay, so this is the idea, and basically you define everything corresponds to field, and similarly and simply you can easily find out without doing anything. You can always find the what the dynamics of fluid. Now what happens is that along with this thing, when you take the derivative, you have to find the autonomous equation x dot, y dot and z dot. So you, in order to do that, you have to define again these parameters, and these parameters are consisting with the different derivative terms, and you don't have to think too much, because these terms can easily be expand in terms of x, y and z. So there is no anything. Now again you have to take the derivative of the potential, and in this case derivative is defined as like v over v of 3 by 2 and some kappa. So we have already defined it. Now here from the Friedman equation you can see you can realize this equation, that it will looks like that 1 minus y square and some complicated term goes here, and z and x square d, and d is having again f comma x, so it will become z comma x part. Okay, so unless and until if you will choose, you have to choose the following. How will you choose your model? Because f is a model part, you cannot work out in general. Okay, so in order to close these variables, we have to first define what kind of f you are going to choose, and then we can expand everything in terms of x, y, and z. Okay, so here are a little algebra like s dot over h square, what will happen, and then we have found this x prime equation, y prime equation, and z prime equation, and these guys are defined like x prime is like dx over h into dt, and this is become dn, and which is corresponds to number of e folds. And in the case, standardized case, if you are working in the Kessence, lambda is always defined to be minus v comma phi over kappa b to the power 3 by 2. Okay, so some people can define in terms of again h and v and so on, so it ups to you that how you want to define your lambda. Again, lambda is kind of parameter which associated with b, d, c, and e, so they are nothing, and it comes out to be for this case it comes out to be only 2 over delta, so again lambda becomes constant. Okay, so so here is this, so you have to first define what is your fx. As we can understand here, as you can see the field equation here, this field equation is consisted L comma phi, and this field equation is actually telling you that this p phi is basically L of phi comma x, and this L of phi comma x has been chosen to be v phi into fx. There are various terms, like people choose fx minus v phi, one can choose square root of 1 minus x square, otherwise you can choose just multiplication. So in this way, in this fashion, because in quintessence it is very straightforward, but in the non-linear terms or in the non-canonical term, this kinetic term is actually multiplying with the field. Okay, so this is not happen in this doesn't happen in your usual case, so that's why this theory becomes very complicated at what kind of a structure we are going to get. So this is very hell lot of complicated when you will define or derive these quantities. So again, just go down. So we have used the two models, we have defined two models. One model is rho to the power epsilon and some form of gamma, which is consist of phi and g of some x. Okay, so you can have rho epsilon, and let us say gamma phi will be considered to be phi square, or gs to be phi, or f phi to the power m and s to the power n. Okay, so we have already defined here rho epsilon phi to pi over kappa, because phi is having mass to the power inverse, therefore kappa is also mass to the power inverse, therefore they will become they will just simply become the dimensionless quantity, and x is also dimensionless quantity, therefore it is just defined beta into x, and alpha and beta are the constant, so it can be absorbed in any way, so it doesn't contribute in anything. Okay, so here is the model that one way you can choose rho square, rho cube, rho 4, and again you can divide by some mass. Let us say you can choose the mass to be m, and this is having it will always make f to m to the power of 4 theory. Okay, now since m is just simply a constant, dimensional constant, so it will not contribute anything in the dynamics. Okay, so you can easily have anything. So we have not written here, you have assumed that whatever the mass, like minus 1 plus let us say epsilon minus 4 plus epsilon, so if epsilon is equal to 1, therefore it must be 0, so consider to be 1. So if 1 is 0, therefore m going to be 0, and you will always have the 1. Okay, so rho to the power 1. So f always be having the mass dimension to the power 4. You can choose whatever the way. We have absorbed that whatever you choose here, m, my dimensional constant, you can just throw it out, because it does not contribute anything, and it does not alter your autonomous system. So for here, as we have already described you have to define your potential. So these are the things that you need to take in care, that these are the things that you are putting and you are guessing it. Okay, so these things people have found out from the string theory, and they have evaluated with respect to the potential part, and they have found the tracking kind of behavior. Like whenever you try to define any field corresponds to dark energy, then we already know that in the early universe, the contribution from dark energy is negligible. Again, in the matter during phase, dark energy was again negligible, and then late time phase, dark energy is kicking the universe, and the universe is expanding and expanding and expanding. So this kind of behavior is called tracking behavior, or we can say that it is scaling behavior. Okay, so that it is scaling the fluid part. So whenever we have introduced the dark matter part, so this dark matter part will be in the intermediate state between the radiation period to accelerating period, there is a period called dark matter part or the matter dominant part. So where if your fluid is a matter type or pressureless fluid, therefore this region will give you the complete picture of the dark matter phase, and again there is an acceleration phase. Okay, we have to consider the model 1 and corresponds to this model 1. So now we have to find the critical points by equating x prime, y prime and z prime to be 0, and here is the fixed point. So we have found 2, 4, 6, 8 and 9. So we have found the 9 critical points. At this critical point x and y is 0, therefore we say that there is no any field, and just only you have the although z is -1. So we say that there is no any field because x is corresponds to phi dot, y is corresponds to v pi, and if they are the 0, we can say that again they are again the field part is 0, therefore it is not a very legitimate critical points. Again you have the constant kind of characteristic like minus plus root 2. Again it is only taking the lambda part, which is 2 by delta in this case, and z becomes 0. So in a lot of things z will always remain to be 0, and we are talking about the model 1 in which we have assumed that here all the points have been evaluated for epsilon is equal to 1. Okay, so it has been assumed that here no, we don't think so. So these here again epsilon to be epsilon, so it is it has been done for the general thing. Now you can see the different contribution of critical points. Now these critical points are very interesting one, and for these critical points z is again 0. It is it is only consisting with the potential terms, because potential is defined with delta. These critical points is having the delta term, and here this other critical point is only consisting with delta, and epsilon term. So it is a very interesting point. And y is again here something delta and epsilon dependent, and here your z term is also non-zero. So we have to understand that what kind of dynamics they will evaluate. So for that we have to first evaluate the omega total, like what is the total equation of a state, and then we want to, and again we want to, for the purpose that we want to evaluate the sound speed, that okay, is sound speed is satisfying the 0 to 1 bound condition or not. Although it is not a very great condition, but again we want to because there are a lot of parameters like epsilon and delta are the main parameters, alpha and beta we don't care about it. So it will figure out to help that which kind of benchmark points you should use to evaluate the theory. So for a point, the omega total 1 minus epsilon. So if you have epsilon to be 0, okay, this omega total will actually giving you 1. So whenever you have omega total, equation of state is 1, it means that your universe is very deaccelerating. Okay, so whenever you have omega is less than 0, means that omega is in negative and omega is less than -1/3, then you can say that our universe is accelerating. But if omega is greater than 0 and if omega is up to 1, then it manifests that your universe is asymptotically very decreasing. And people are doing research to find out how the early universe, how much was not accelerating or it was in deaccelerating phase, that the evolution of the universe was damn slow. Okay, so that is the idea. So if you have the epsilon to be 0, then it is going to be 1, and as you are increasing the epsilon to be 1, let us say again if epsilon is 1, then this point will actually contribute towards the method part, and more than epsilon to be 2, let us say 2, again this point will become the accelerating part. Okay, so now at some point it can easily easily go through maybe epsilon to if epsilon is 3, then omega total can be -2, so it is more accelerating. But here is the glitch that cs squared is minus epsilon. So if you take any positive value for epsilon, then cs squared will become negative, and we can say that since cs squared the sound speed is negative, so this theory cannot hold good. But the thing is that it will be very interesting to see that epsilon can be negative. Okay, so if you can take epsilon to be -2, then what happens is that cs square, or let us say epsilon to be 2 and cs square can be negative, we can say that okay, we throw away this quantity and omega total becomes -1, and you can take epsilon to be -2.12 and so on. So this point can cross the phantom barrier, and you can investigate more about the things. Okay, so now if you take more epsilon to be negative, so So what happens is that your the interaction part will become like this. Suppose epsilon to be -2, then your f becomes 1 by rho square, and then again phi and x. So what happens is that this point is actually telling you, because omega total will become greater than 1, so it is actually manifesting the great deceleration of the universe, that at the early phase, if your energy density was something dominated and this phi and x were not dominated, so this omega total is actually exhibiting the very deceleration phase of the nature, and this may corresponds to the early phase of the universe. So this is a very interesting part. Let us see about this b plus minus. Then it is giving me 0, and cs square is 1 by 5th, so we can say that okay, it is a legitimate point. It is giving you the matter part. And c plus minus, again, it is in a hell kind of thing, like it is depend on delta prime delta. You will we will see in a minute that it becomes clear when we choose the delta value and the epsilon value. So suppose epsilon is equal to 1 or epsilon is equal to 2, it will become clear that when omega total can become 0 or not. So I have defined here that if delta is not 0, then omega total can be negative. The how much is negative we will see in the phase space plot. So now here that we have used the stability condition for omega is equal to 0, that what could be the stability condition. So for these points we have found the stability condition. So here it says that if your point A, epsilon could be anything and delta could be anything, it becomes undefined. It means that we cannot define the stability corresponds to this point. Now for this correspond for B, if epsilon is greater than 3 by 2 and delta must be follow this constraint, then there is a little window for it to become stable, otherwise it will become saddle point. Now for c plus minus, then again if epsilon is greater than minus something or epsilon is greater than minus 1.5, then these points can become a stable point, and for delta 1 to 3 you can have the stability. Now similarly the other points, now if you take the other points and your epsilon is between the 1 and 0 to 1.5, then you will have the stable point. And if your epsilon is greater than 1.5 and delta is lesser than, means that you take -2, -4, -6, -8, or if delta is greater than 4, 5, 6, 7, then this point becomes stable. Okay, now for E minus plus, because it is depend on delta and epsilon, so here we have taken that for here epsilon and 1, then if you have the epsilon and delta is 1, you will have the behavior could be saddle, and for 1 and 2 it is stable, then 1 and 3 it becomes saddle, saddle, saddle. And then if you take the negative sign of epsilon, then again it will give you the stable kind of thing. So here it is a very interesting thing here, that this point can become stable. So it could be different kind of, it will play a different kind of dynamics here. Okay, so as you can understand here that omega total can become negative for epsilon is again less than 3 by 2, so it is actually but taking care of negative values. So if we have the minus, if we have minus 1.5 and delta is 3, it is stable. So it says that this E minus plus can render stable solutions. Okay, so these are the things, these are the description of the whole points that I have described to you. And now try to understand the dynamics. What we try to understand that what could be the phase space, and this phase space is defining by these variables that we have defined x, y and z. But when you define the x, then you can see they are at phi dot, and phi can take any value between plus infinity to minus infinity. In some sense x become minus infinity to infinity. Similarly y can also become minus infinity to infinity, because it is only because it depends on the potential, and potential is like 2 by phi square, and again phi can take any kind of value, so it is legitimate to it can take any value. And again simply thing happens with the z interaction, so z can be negative and positive, it doesn't matter. Now the constant is real constant is putting from the Friedmann equation that sigma square is corresponding to the critical density of the matter, and this critical density can be 0 and to be 1. It cannot be negative, because we understand whenever we define the field and the fluid, so what happens is that we have to take the energy density of those field and fluid to be positive quantities. But this criteria does not fit with your interaction, because the interaction term is kind of something which is the internal mechanism. We cannot observe what is going to happen in this interaction and so on. So it can be negative and positive, doesn't matter. It just it is it is the mechanism by which the energy is transporting between the field and fluid. So we can have the z minus infinity to infinity, or the, or it does not, or the or omega phi or omega m always be 0 to 1, and omega phi, which is critical density of the field, has to be 0 to 1, but not with the omega interaction. The critical density of the interaction part can be minus infinity to infinity, no problem. So far we have this kind of thing, which is, you know, real constraint, but the problem is that we cannot constrain the phase space in some kind of shape. Okay, so what happens is that whenever you have these kind of thing, you can, you know, encapsulate these, you can transform these variables into something more more, you know, general. Like for an example, if you define tan inverse of you know, pi by 2 or tan pi by 2, we know tan pi by 2, tan 90 degree becomes infinity. So if you take tan inverse of tan pi by 2, so you can have tan inverse of pi, so it will become pi by 2. So tan inverse of phi is always become pi by 2. So what happens is that we can take tan inverse in this side, and we define that, let us assume that arc of, or tan inverse of x is capital X, tan inverse of y is capital Y, and tan inverse of z is capital Z. So in this way our phase space is now constrained between pi by 2 to minus pi by 2, or you can also define your hyperbolic quantities like exponential of hyperbolic of x and so on. So these are quantities, because in no way we can constrain the phase space, and these are not very much compact, so we have defined these variables to compactify our phase space. So now this phase space is looking like that, this quantity is x, and this is z, and this is y. So again, these plots are very complicated, and it has, you know, taken the hell lot of, you know, job to plot these kind of things. Now this is the phase space, and in the phase space you can see that it is the symmetric across x, and you can see that whatever is happening here, no trajectory is crossing this x is equal to 0 barrier. Why it is? You can see that x is equal to 0 is actually giving you the invariance. So no any trajectory for any initial condition can cross x is equal to 0 barrier, because our system have this x prime is equal to 0 when x is equal to 0. Okay, so this is x small x. So whenever here you have this kind of a scenario, then you can say that this is an invariant manifold. So x here is acting like an invariant manifold. So whatever is happening in the positive direction, it will never affect in the negative direction, and vice versa. So here we have plotted for epsilon is equal to 1 part and epsilon is equal to 2 part. Now you can here see that this E plus and E minus part are showing you the stable accelerating point. C plus and C minus are the points which is corresponds to the phantom point, because here the omega total is less than minus 1, and less than means minus 2, minus 3, minus 4. So here that these trajectory are coming from somewhere, coming from some past, and then it is going through this point D and B minus, and these D and B minus, they are corresponds to the omega total non-accelerating part. It may be 0 or it may be 1/3. So here it is 0, and then it is going towards E plus minus, and E plus minus where omega total is minus 1. So it is between minus 1/3 to minus 1. Okay, so it is never crossing this point is never crossing the phantom barrier, and here it is an again isolated stable point. So all the trajectory, some trajectory is going here for different initial conditions, and some trajectory is evolving from some other thing, or maybe it's coming from the past and going to D plus and B minus, which correspond to the unaccelerated portion, and then eventually attracted towards E plus minus. Okay, so that is the scenario is happening like here. But on the other hand, if you look at the epsilon is equal to 2 trajectory, it means that it is originating some point. Again, C plus and C minus are kind of isolated stable point, while E plus and E minus is giving you the 1/3 kind of scenario. It means that the Kessence or effective field is actually giving the 1/3 characteristic, and here D plus minus and D and B minus, they are giving you the omega total to be close to -1. Okay, so here you don't have any critical point which is actually giving you the dark matter portion, but if any critical point would have been, then it is corresponds to this kind of this point, where it shows that after evolving from the 1/3, it is going towards the matter epoch, and then from matter epoch it is attracting towards the accelerating point. So this is the whole scenario, that as you are increasing your epsilon is equal to 2, we have not plotted here epsilon is equal to -2, so the dynamics is very smooth and very interesting. So it is basically connecting the early universe to the late time cosmology, and hence you see different kind of dynamics interplaying the whole scenario. Okay, now we have also evaluated some part like omega total and cs square in this case. Now here you see that omega total is in early region is actually starting from 1/3, and this cs square plot, and this cs square is decreasing from 1/3, and when omega total is passing this 0 point. Now this 0 point is corresponds to the unaccelerated region, and here it is showing you the dark matter kind of behavior, and here it is actually going towards like 0.1 or 0.2%. And again this omega total graph is basically converging towards, let us say, -0.3. So in this case, if you have a specific kind of delta is equal to 2, then this is not producing enough acceleration. But on the other hand, if you have in the epsilon is equal to 2 case and delta 2 case, then what happens is that it is basically starting with very deaccelerating phase, and cs square is again greater than greater here, and then going through the 0 phase, and then again it is converging towards 0.4. So it is not also contributing great accelerating. But as you will increase the delta value, let us say it is 10 or 20 or 50, then this graph will goes like this. So we will see in a minute that if you take the model 2, then again same thing happens, that C plus and C minus are the phantom points, and here you can see that A plus is actually unaccelerated regime, and B plus it maybe corresponds to matter phase, and A plus is again saddle point, and in this case D plus and D minus are the accelerating point, which is corresponding to the -1%. And for here you can easily understand that for n is equal to 1, m is equal to 3, delta 10, we have evaluated the omega and the cs square plot. So it is starting from 1/3, going to the sharp change. Okay, so this omega total is for some time it is actually non-accelerating, and then going towards 0 phase, and then hitting -1, and then again converging towards -0.8. And if you use the very larger value of delta, for example 2000, then it is actually converging towards -1 point. Okay, and similarly in the late time phase, the cs square sound speed also becomes 0. So this sound speed is very important quantity if you will investigate, if we have not investigated thoroughly, but this sound speed is very important from the perspective of large scale structure. So this is whole. So I hope everything is fine till now. So we will see you next time, and for now, this is Nonminimal signing out.